very much, Patrick. And thank you. It's an honor to be awarded, and it's an honor to present my research, the expanded part of my research, because the poster I presented was it's quite limited space. You have to cut off a bit of it. But I also realized that I have a lot of time here, so I thought I would first start off to just talk about the background of this research, the research that I've done with my colleagues here in Umeå that has led to this paper that resulted in a poster. So we're in Sweden. I'm at Umeå University at the Center for Demographic and Aging Research up in northern Sweden, where we have these cold climates. As you can see here, for example, this is me in this small sled when I was an infant, and that's a bit of no, not myself, but at least the temperature exposures and climate vulnerability of infants I'm going to talk about today. So when it comes to climate vulnerability, what I mean by that is the risk of being negatively affected by weather, and that could be heat waves, cold waves, extreme cold, rainfall, or floods. And the vulnerability to these climate events, that would vary by individual and social factors. So together with a number of researchers here at the center, we have looked at different aspects of this among infants, and mostly on neonatals. And specifically, we have looked at both physiological, behavioral, and social factors in relationship to temperature and seasonality, but mostly to temperature and mostly to cold in these cold climates that we have up here in the north. And to add to that, we have looked at this from a historical perspective, how it was historically in the 1800s, 1900s, when we had much higher infant mortality also. So once it comes to physiological associations, one of the most important factors is gender, and this is from a paper together with Lena Karlsson, Ali Lundevall, and Barbara Schumer that was published now 2 years ago in Environmental Research, and this is on neonatal mortality, so up until 30 days of life. And here, this is also in northern Sweden, so here we find that it's primarily among boys that there is this temperature vulnerability. The colder it is, the higher risks of death these boys have, and also the warmer it is. But we have this strong cold effect among boys, and not really for girls. They seem to be much more resilient. And when it comes to behaviors, we have looked at difference between Sami and sedentary populations. So the Sami population is the native population of the northern countries, and in the 1900s, majority of them lived as nomadic grain herders. So in here we look at differences in infant mortality for in winter seasons, spring, summer, and autumn. And one thing you can find when looking at these differences between the Sami and sedentary is that the Sami population had higher risks of death in the winter, although they are more, so to speak, a population that you might assume would be adapted to these type of environments. But one of the reasons for this, at least speculatively or probably, is that they lived in lavvos, these tents, where they had an open fire in the middle. So infants were much more exposed to air pollutants. They were also, in general, much more exposed to extreme cold temperatures compared to the sedentary population. So such side effects that could be things like living standards or socioeconomic status and so on. So in a paper in Population Environment, also 2 years ago, we looked at the variation between different social groups. Although we didn't find any specific pattern, there wasn't this social gradient, for example, that the middle class would be better than the working class. You find these certain types of pattern, for example, that infants from worker families had this higher vulnerability, greater vulnerability to high temperatures. But overall, this is not this social gradient is not always the case to be true in historical populations. For example, men of higher classes have had higher mortality in 1800s than working class men, for example, which is not true today. Let's see. The idea of this paper is to continue on this research, to look at more about the mechanisms or what the different parts of these climate vulnerabilities, and specifically to infectious disease mortality in relationship to temperature and seasonality. And this can be very much seen as a pilot study, a test study, because it's a very small sample population. I need to expand this and do this for larger groups or larger populations that we also have data for, but wasn't available at the moment there. But this is in the Swedish 19th century, 1800s. So we know that climate conditions such as ambient temperature can be crucial for infants' vulnerability to infectious diseases. So exposure to very cold climates, such as my son here hanging on the back while I shoveled snow, can increase the risk of getting an infectious disease, or there seems to be this association at least. And when it comes to the link then between temperature and disease mortality, we know from modern research that, for example, water and foodborne infectious diseases are much more common in the summer, warm temperatures, because these pathogens thrive in warm temperatures and reproduce much more. So the exposure to these pathogens increase. And in the winter, there is this case that one lowers one's immune responses to viral infections in cold climates, essentially, which would lead to greater numbers of airborne infectious diseases. But temperature also correlates with seasonality, and this becomes very evident in northern Sweden, when it can go from very, very cold temperatures in the winter to relatively warm temperatures in the summer. But that also, the seasonality also affects behaviors. When it's cold in the winter, we increase our indoor activity and thus increase exposure to viral infections. And in warm climate, warm during the summer, we see more social interactions, more animal interactions as people are more outdoor, which increases exposures to water and foodborne infectious diseases. So historically, then, we also see this strong seasonal patterns for those studies that have been done on seasonality of infant mortality or mortality in general. Primarily, there is this winter peak in mortality across Europe. There are also some studies have also find this summer bump primarily in large urban centers historically, but that is also true today, that we have a high mortality in very warm in the summer. So the aim in this study was to investigate the association between the infectious disease mortality among infants and ambient temperature, the first part, and secondly to seasonality, using then these historical data from Sweden from 1868 to 1893. So the data we use here comes from a database called Popum. It's a longitudinal database that stretches from the 1700s until about 1900. We also have data stretching further on until the 1950s, which in turn can be linked to modern register data. But this is the data we use here. And this data is composed of these linked historical church records. So we have historical church records such as baptism registers, birth registers, death registers, catechetical examination, migration books, and those. These have been digitalized and then linked on individual levels, so we can follow individuals, know their parents, and so on. And the sample here is consists of 14 parishes surrounding this town of Sundsvall, the red area here, which sits on the Gulf of Bothnia, geographically centered in the located in the center of Sweden. But it's also part of what you would call northern Sweden. Yes, so this was also this booming sawmill industry town in the late 1900s. The blue areas represents like the industrial parts of this region where the sawmill industry grew quite a lot at this period. Yes, and from this data we collected the data on birth date, place of birth, date of death, cause of death, and last observation data. That's more than 47,000 births. So then cause-specific mortality and infectious disease mortality specifically, we gathered from these, or they come from these death and burial registers. So when a person died, they noted the cause of death, and the type of causes or the nomenclature used was then stated in these regulations, which we can see on the other side here, called Svensk författningssamling, this laws, regulation text essentially. And during these, from 1860s onwards, there were two systems of who was responsible for these death certificates. In the cities and towns, the death causes of death were certified by a doctor, and in the rural areas, it was the clergy who did this. But they used the same regulations and the same nomenclature to write this down. These in turn have then been coded into the ICD-10H coding system. And that's based on the modern ICD-10 system, but adapted to fit the historical causes of death. For example, like teething is, or dying from teething related things is not related to like dentistry. It's more likely to be related to fevers, for example. Yes, so the idea is to capture both like these, to make it this coding system, but also capture the historical context of that. How is certain diseases described? Yeah, this cause-specific data, or this ICD-10H codes, has then been categorized into three groups: airborne infectious diseases, water and foodborne infectious disease, and other causes. Airborne, these are diseases such as whooping cough, pneumonia, smallpox. water and foodborne infectious diseases are gastronomical inflammations or infectious diarrhea. And then we have other types of causes of death, convulsions, external causes, birth disorders. And then we have a large group of unknown causes of death. And that was the majority of the causes of death in the beginning of the study period in the 1860s. Most of them had no code. And primarily this is also this comes from the rural areas where the clergy was responsible for registering, were much more likely to have a cause of death in the town. Temperature data is collected from the Swedish Meteorological and Hydrological Institute, SMHI. And we collect data from the Härnösand weather station that's 40 kilometers north of the town of Sundsvall. From 1868 to 1892, so they have these thrice daily temperature measurements. And those measurements stretches from minus 33.9 is the most extreme cold, and then plus 27.5. And from as daily means also. And in the coldest months, we have a median temperature in February of minus 5.1, and in July, the warmest month, we have a median of 50.9 of these daily means. And then for each day between 1868 and 92, we have calculated the average daily temperature exposures over the past 14 days. So for each day, we know what was the temperature the previous day, 2 days back, up to 14 days back. And then to test the association between temperature and infant mortality and seasonality and infant mortality, we use time series analysis. And that means that we calculate the number of deaths in a certain age group by day, and then model the association using Poisson regression. So we take this, I have 3 age groups from 0 to 13 days, 14 to 30, and 31 to 365 days old. And then we adjust these measurements for time trend, and then for seasonality and lag temperature exposures respectively. And also, which is not seen here, also the place, the actual location is also adjusted for. So you compare within parishes, so to speak. Yes. But one issue when then looking to the association temperature is that it's non-linear. It's not that it's the colder it gets or the warmer it gets, it's the risk increases. But it often has this, for example, this hockey shape pattern that can be seen in the top part of the figure, for example. And to capture that, we use this this distributed lag non-linear models framework developed by Antonio Gasparini, among others. And when it comes to all-cause mortality, which we look at first, we specify the association as a cubic spline with 4 degrees of freedom, which essentially then fits a curve through this association, or this temperature mortality association. And when we turn to cause-specific mortality, we specified or simplified it into a threshold function. So at this given a certain threshold in this temperature span, we say that it will be linear, the association below or above this threshold. And then in turn, we assume that the effect of temperature on mortality is lagged and non-linear also, this lag effect. Essentially that after exposure, for example, to heat, it would take a number of days before you actually die from the infectious disease you got due to this heat exposure, or this infectious disease exposure. And this association is specified as a cubic spline with 4 degrees of freedom, and we set the knots at logged intervals. That means that we expect most of the variation from one day to another to be in the first few days, like from the first to the second days after extreme heat, we would see more variations than from the 9th to the 10th. Then would see very less variation in the effect of lag time. Yes. So this is just mortality rates. So we have more than 47,000 births and then about 6,500 deaths. 456 of them are water and foodborne infectious death, and 898 is airborne infectious deaths. So not that great of a sample, but at least some to work with here. And when it comes to all-cause mortality, we see this more hockey-shaped pattern. It's higher with very low temperatures and very high temperatures, and it reaches some form of minimum mortality. Here it's quite wide. Now these are, I think it's -6 to about 3, the minimum temperature. +3 is the minimum temperature. Something strange with my legends. I think that's more correct. And for airborne infectious disease, we see high mortality in cold temperatures and lower in warm, and the opposite for water and foodborne infectious diseases. It's in heat, you see this as one would expect. Just looking at all-cause mortality, and this is from the models. And we describe the effect here as incident rate ratios from the Poisson regression. So these are more like relative risks. And this is the given like the 14 days past temperature exposures, what would be the relative risks. And then you find this heat effect at +15 compared to +5, it's about 25% higher risk or something like that. Yeah. And then breaking it down by cause of death. We have in the first on the left, it's other causes than airborne infectious diseases, and the third is water and foodborne infectious diseases. And this is comparing then the effect of a temperature exposure compared to this threshold point, which is set at some form of breaking point in the where the association seems to shift between cold and warm temperatures. And what of note here, or what I want to take from this, is that it is primarily these water and foodborne infectious diseases that we see this increased risk at high temperatures, while not really for airborne infectious diseases. So at +10, 20, it's more than 4 times higher risk, 5, 6, 5, something like that, times higher risk of death. And looking at then the lagged effects, it's primarily for water and foodborne infectious diseases at +20. You can see that after around 10, 11 days, it starts to increase the risk of death, which would be expected that you have exposure to an infectious waterborne infectious disease due to heat exposures, and then it takes a long time for incubation time and then time to actually kill the infant. But otherwise, there are no, so to speak, significant effects of these lagged exposures. So then turning to seasonality. So here we see this is also from the models, adjusting for temperatures, place of birth, and the overall time trend. And first is the unadjusted fit, and then the adjusted one. So here, seasonality is measured as the day in the year from February 1st, which is assumed to be the coldest month generally, to the last of January. And in the unadjusted, you see this winter peak. It's highest in January, February, but also this summer bump in August at some point. But adjusting them for temperatures, place of birth, and a yearly trend, this summer bump disappears, and the winter pattern becomes even stronger. And when we break this down by infectious diseases or causes of death, you find two different patterns. And what is interesting is these 4 lower bars there: airborne infectious diseases and water and foodborne infectious diseases. So for airborne infectious diseases, adjusting for temperature, the seasonal pattern becomes stronger. We have quite great confidence interval, but the pattern becomes stronger. It seems to be an even stronger seasonal pattern. While for water and foodborne infectious diseases, the opposite seems to be the case here, that the summer bump is reduced. So the main findings here is that there seems to be a strong association between high ambient temperature and all-cause mortality and water and foodborne infectious disease mortality among this population. And that airborne infectious diseases is not related to low temperatures as much, but rather to seasonality. It's that it's winter, it seems to be more affecting the high numbers. And water and foodborne infectious diseases shows the opposite, strong relationship to high temperatures and not as much to seasonality. So that's not really maybe what you would expect, especially historically. Families had quite limited means to protect their infants from cold. They did not have the same means to heat their homes, for example. And due to reduced resilience from viral infections, we should see that. But there seems not to be this association, at least here, between cold and airborne infectious diseases, but rather the effect of actually crowding together in houses and apartments. High temperature seems instead to be quite related to infectious disease mortality, water and foodborne infections. This seems to correlate then with or be in line with that. That warm temperatures improves the survival for bacterial pathogens, and that's what we see here, and probably why we see these these summer peaks in 1800s and 1900s urban towns that have been seen in historical demography. Yes. So human behavior seems to be important, not only temperature exposures, and this could be, but some things to take of note. It could also be quite different in urban environments. This is quite sparsely populated area, even though we have this town of Sundsvall. It's quite small relative to Stockholm or the urban centers of Europe at that time, or the urban centers of today. So there could be no effects due to quite low population density here. So the strengths and limitations of this study is primarily that the strengths is that we have this cause-specific mortality data for a 19th century population. But one of the limitations is that medical knowledge change. However, like the same, we don't have the same ICD system for the whole time period. They don't have the same nomenclature or the same ideas of diseases and causes of death. But what is to say is that it's relatively easy to at least find these infectious diseases if they die from smallpox or something like that. But also notice that it's quite small sample sizes, and a lot of unknown causes of death. And then there's also these other factors. There's no data on humidity or indoor air pollutions, which highly correlates with temperature, seasonality, but it's also one factor behind a lot of highly related to one's climate vulnerability. But with that, I think I can conclude. And I just want to say thank you for listening. Yeah, that's it. Even if you have any questions, please feel free. This is still ongoing research, and I hope to continue this.